Hi all, welcome to the first part of the video lecture on asymptotic analysis. See in this course algorithm analysis and design. So far we gone through the basics of analysis, right? So the main concept we studied is something called as a step count analysis, right? So in step count analysis, hope you remember what we done is, so we started counting all the basic operations. So what we need is a platform independent way of analyzing any algorithm, and we should be able to compare different algorithms for a given problem. So that is the overall um, goal, right? So accordingly, so we come up with this step count analysis, and what we done here, basically we counted all the steps in the sense the major operations we counted. So the number of comparison operations, right? Say number of increment operation, number of assignment operation, like that everything we counted in detail. So this is something which is trying to provide an abstraction, right? Abstraction in the sense, so if you are doing the actual analysis, say in exact, if you are trying to express the running time in say seconds, and also that will be something depends on the platform. But when we are writing like this, you can simply compare different algorithms, so based on this number of comparisons, so not based on the real time. So when you actually do that analysis based on the say time, say in seconds, so that will depends on the platform, so we don't want it, right? So that is why we move on to something like this. Then I told you, if you want, you don't have to focus, so same line you focus, for example for loop or something, there will be increment, assignment, comparison, or some arithmetic operation. Many things will be involved. Now out of them, what do you focus on this something called as a dominant operation, right? So most of the algorithm we saw so far, this comparison is found to be a dominant operation, especially the array based algorithms, right? Something, many things we discussed. So focus on that, and you come up with the count, so that I'm saying that in a particular line, this comparison is happened some 10 times, increment and assignment are 10 or something near to that 10. In that case, when I just focus on comparison, uh, basically what we need is we want to compare two different algorithms. The other algorithm will also have this comparison as a dominant operation. So that time, when you are counting comparison in that second algorithm, so you are getting some, your the final analysis you are going to express as step count, which is actually a function of the input size plus, and it's going to count the number of comparisons, something like that. So when you focus on dominant operations, say comparison, so that depends on the type of algorithm we are having, but mostly we can take this comparison as the dominant operation, and that type you can see that it is some more, uh, it's providing some more level of abstraction, right? Something like that. So both are fine. You can either do analysis in a very detailed way where you are comparing, you are counting all basic operation, or you can just focus on the dominant operation. Anyway, both are fine. Finally, you will get this running time. Say in the last video lecture, I think we discussed that insertion sort algorithm, where you get some set of constants, right? Some set of constants into some n square term plus some another set of constant, right? Let me write some set of constant. Anyway, we given different names for the constants. Okay, something like this with some n and last some another set of constants. So something like this you got, right? Hope you remember. Say okay, I'm just right. And then what we done is, so these all these constants you expressed using a single constant, say capital A something. Okay, so here all these constants you expressed using another constants, something like this, and here you expressed using something like that. And then you return the same step count analysis as something like a n square plus b n plus c. Okay, so this is what we saw so far. Now from this point, let me tell you, so we are moving on to something called as the asymptotic analysis. So asymptotic analysis, basically it focus on the dominant term. So here it is like a dominant operation, accordingly you are giving this analysis like this. So if you are looking at this here also, I have some kind of more abstraction in the sense when I'm writing like the time taken is C1 plus C2. So all these constants actually, I don't know. Just depending on the actual platform we are having, this constant will vary. So here itself we can see some level of abstraction. So when you're some adding all this constant representing using some other constant, again there is one more level of abstraction, right? Now we are moving on to one more level of abstraction through this asymptotic analysis, where the entire expression, you will say like this n square, this is a polynomial of degree n, I mean degree 2, right? So it's the dominant term is something like n square, so the whole thing you express like some order of n square, like that. So what is this order of, or this notation big O? We will see the formal definition. Anyway, for the time being, it's a notation for representing asymptotic analysis particularly. So in this video only we will see what does this one, the mathematical interpretation of this big O. Okay, anyway, so what I done here is important, because let me just tell you like so what I done is, compared to this particular term, there is a linear term say bn, and there is a constant term say c. So these two things you can ignore. Okay, so just focus on the term which is having the highest degree, like that. Okay, now here also this constant coefficient also you can eliminate, and finally it is coming like this n square. Okay, so you may be wondering why it is so. The thing is that if you are focusing your analysis like you just give some value for this, what is n? N is the input size, right? Suppose I am talking about an array with 10 elements, then this an square plus bn plus c is something like some constant into 10 square plus another constant into 10 plus some other constant. And when you are writing it like some n square, like say 100, you may not be convinced. Like for example, let me tell you, you got the running time of an algorithm like I'm giving some value for the constant, some random value I'm giving, plus 6n plus some 3, like that. Okay, then I'm saying that this is equivalent to some order of n square, right? Now when I'm substituting some smaller value for this in n, like say n is equal to 5, you can say that this is something like n square is 125, 125 into 5, sorry, 25 into 5 will be 125. So it is like 125 plus 30 plus 3, right? 158, right? Yeah, this is like 155 plus 3. Yeah, here I am getting something like n square. N square is 25. So you may feel like this is a much bigger quantity, right? Like I am getting on to 58, which I am reducing to something like 25. I may not be convinced at this point. Okay, now what I want to tell you is like so why I am getting that 158 like a bigger quantity, because of that constants and other terms. So it matters when the input size is small. Now what we are going to do is we are actually, in general, we don't want an algorithm which will run only for smaller input, right? So what we are for interested is, we want some algorithm which run nicely on some very large size input, like so let me take an input like say 1 lakh or something bigger than that, right? So now at this point you will get that difference, like so here I'll be getting 1 lakh square, here it is just 1 lakh. So 1 lakh, you know it, right? So as the input size increases, so it can be something like or 10 power 9 or 10 power 10, some very bigger value of in input size you assume, and that time you can see that these two things are almost same, like that. Okay, so the effect of this smaller constants are less compared to that n square term, because n square is a quadratic term, right? N is just a linear term. So whatever be the value of n, that 6n will be some 6 times n only, but here you are getting its square, right? So that will be very very bigger number. So assume a very large value of n, how much big is your n, that much bigger will be this n square compared to n, and in that time the what I can tell you, the effect of that 6n is something you can ignore. Similarly, the constant 3 also you can ignore, and that constant coefficient 5 also you can ignore, something like that. So the same thing will happen with the other algorithm also. So if you have a say 2 algorithm for a given problem, see I am saying that this algorithm 1 and this is algorithm 2. Okay, then I am saying that algorithm 1 is having a running time like say 5n square plus 6n plus 3, so that you will round off it to order of n square, right? And algorithm 2 is having a running time like 10n plus 3. Okay, so you can say this is something order of n. So now you can say that the first algorithm is a order of n square algorithm, in the sense it's a quadratic kind of algorithm. Second one is an order of n or a linear type of algorithm. So you it's at this point it's very clear, right? So the n square algorithm is going to take much more time than that order of n algorithm. So what we need is an algorithm which is something like this. So okay, so this is much more, so we prefer this algorithm. So A2 is a much better algorithm compared to so A1. Now you are able to tell this I mean comparison between these two algorithm, like you are able to say like A2 is more efficient than A1. So by looking at the dominant term only, so you are not focusing on that constant or other terms and all. Simply 10n plus 3 is a linear function of n, so I can say that it is order of growth. So this is something we call as the what is the order in which the algorithm running time is growing as a function of input. Okay, so that is what we call as order of growth. So here I can say that see order of, let me write here anyway, I used the whole space. Order of growth of algorithm A2 is more than A1. Okay, it's much more than A1. So compared to A1 is growing, sorry, A1 is more than A2. Fine, sorry. Order of growth of A1 is more than A2. Okay, because when A2 is growing, order of growth of the algorithm A1, which is order of n square, right, is much more than that of A2. A2 is growing in a linear fashion, where A1 is growing in a quadratic function. So that about it. So I am having this conclusion by looking at the asymptotic analysis only. So I am not focusing completely on the step count analysis, that may create some confusion. I don't want it, just focus on the dominant. So this is the whole essence of the asymptotic analysis. So this is some one step beyond that step count analysis. From that step count analysis, you will get the running time of the algorithm as a function of n, something like something like this. Okay, so from that point, this order of growth is what the asymptotic analysis is focusing. So as the order of growth of algorithm A1 is much more than A2, you will prefer A2. We always need an algorithm which is having order of growth less, right? So that is the first terminology we are having. Observe that the simplification of abstraction that we used in insertion sort of, hope you remember in the last video we discussed it. So first of all, we ignored the actual cost. Actual cost in the sense, what is a real cost when you are running on a given platform. Instead, you express it as some constant. We don't know. Okay, that constant value will vary from one platform to another. So that is the idea we done. I mean we used, right? So then the worst case running time we expressed as something like a n square plus, hope you remember this, bn plus c for some constants a, b, c. Then but so here so the actual cost you ignored, and or you represented it using some constant ci, and also the so when you are writing like this, there is something called as an so this ci is an abstract cost, right? Ci is an abstract cost, is it is not representing the actual cost, which is abstracted by a constant ci. I am writing in general like that, and that depends on the platform, like that I am telling. So now the ci is an abstract cost. Now in the next level we ignored that abstract cost ci also, or we added all these constant together and we express this as something like a n square, and I am saying that a is a sum of a set of constants. Okay, so that also we ignored. Now if you want for one more level of abstraction, okay, or the further simplifying abstraction is what we call as the rate or the order of growth of algorithm. So this is important. So what is so this is something what we are doing in the asymptotic analysis. Okay, so asymptotic analysis is the most abstract form of analysis, something like that. So it ignore all the background details, all constants, all smaller terms, everything, and it will just focus on the dominant term. Okay, so this is here I can say that it is trying to express the rate of growth of the algorithm running time, or order of growth of the algorithm running time. Okay, so the first point is it considers only the leading term of the formula. So that is important. So what is the leading term of the formula? In our example, it is a n square, right? Just focus on that. Since the lower order terms are relatively less significant or relatively insignificant for large value of input. That is very important. Do your analysis. So don't say like for n is equal to 5 this is a scenario, so I'm not going to ignore that. I will focus on right. Okay, so just assume some bigger value for n. Okay, and that time only you will understand what this kind of an how this kind of an abstraction is going to help you. Okay, because when I am writing like this algorithm A1, when I have an input of size 1 lakh, it is growing like 1 lakh square, but here it is just 1 lakh only. So this is much slower algorithm A1. Okay, so that kind of comparison is what we are doing ultimately. So for that, this kind of a abstraction is going to help a lot. Okay, so that about it. So for do the analysis for large value of input size n only. Okay, and where you can focus on the dominant term or the leading term. Let me tell you. So I use the term dominant, or let me call it as a leading term. Okay, so just focus on the leading term. Now that is the first point. It also ignores the leading term's constant coefficient. So what is our leading term? It is a n square, and it is having a constant coefficient a. So that also you ignore, okay, because that also not going to have an impact for large value of n. So that is the reason. So it also ignores the leading term's constant coefficient. Also we will be ignoring, since the constant factors are also less significant or insignificant for large input. So always we focus our analysis for large input only. So that is important. Okay, so the worst case running time of insertion sort is found to be order of n square, because we got a abstracted form like a n square plus bn plus c. From that is the result of the step count analysis. From that point, using asymptotic analysis, we reached this conclusion. Its order of growth is order of n square. Okay, so the worst case running time is basically the order of growth. So that is important. One algorithm is said to be more efficient than another if its worst case running time has a lower order of growth. So this is important. So here this algorithm A1 is having order of growth n square, A2 is having order of growth n. So A2 is having a lower order of growth, say that says that A2 is more efficient, right? So one algorithm is said to be more efficient than another if its worst case running time should have a lower order of growth. That is what we need. Now when it comes to asymptotic analysis, okay, so that is what we saw. It's basically focus on the order of growth, right? So the order of growth of an algorithm running time gives a simple characterization of the algorithm's efficiency, right? So because we don't want any complexity, all constants, all smaller terms, everything we are ignoring. So it is a simple characterization of algorithm's efficiency, and also allows us to compare the relative performance of the alternative algorithm. So in that example A1 and A2, so we can find which is better, relatively which is better, like A1 is taking n square time, A2 is taking n time, so A2 is better, like that. So once the input size n becomes large enough, so the full impact is only for, so if you want an efficient algorithm for smaller values of the input size, then you don't have to do asymptotic analysis and all. Just focus on step count analysis and say which is better. But here it is applicable only for large input size. Okay, so keep that in mind. Okay, for example, for large input value, merges out is taking n log n time. Hope you remember how it is taking n log n. That derivation we will see later. And n square time is taken by the insertion sort, and out of them n square or n log n, which is smaller. Here it is n into n, right? So here it is, this is n into n. So here it is n into log n. Okay, so n and same, but what about this log n or and n? Log n is very small quantity, because if n is 1024, log n is just 10 only. So by default log, what I mean is to the base 2. So that is typically what is represented by LG. LG means logarithm to the base 2. Okay. So LG of some x is equal to logarithm to the base 2. So that is by default, right? So that about it. So like that you can compare different algorithm by looking at their order of growth. So this is basically what is happening in asymptotic analysis. Now for large enough inputs, the multiplicative constants and lower order terms of an exact running time are dominated by the effects of the input size, right? So lower order terms as well as the multiplicative constant, the constant coefficient, everything are of less significant, or you are removing it because input size is very large, and the overall running time will be dominated by the dominant term, okay, the bigger term in the expression. So when we look at input size which are large enough to make only the order of growth of running time is relevant, and we are studying. So when we focus only on order of growth, right, and parallelly we assume some large input size. If these two things are true, I can say that the type of analysis I am doing is the asymptotic analysis. So it is trying to say the asymptotic efficiency of different algorithms. So two things are important when it comes to asymptotic analysis. First thing, we should focus on large input size. Okay, and second point is we have to focus on the order of growth of the algorithm and not the actual step count analysis. Okay, so these two things you can keep in mind. So that is, we are concerned with how the running time of an algorithm increases with the size of the input, say in the limit, as the size of the input increases without a bound. So for a given value of input size, how the order of growth is varying, and don't say some infinite value of n. Okay, but actually it can grow in like infinity, but you can assume a very large value, and accordingly you can say which is better, like that. So usually an algorithm that is asymptotically more efficient will be the best choice for all but a very small input. But suppose you have an application which where you will focus only on small input, then asymptotic analysis is not going to be a good choice. Okay, asymptotic analysis will work only when you are focusing on the algorithm efficiency with respect to the size of the input it is handling. So for large size input, you have to say which is better, right? So in that case only it is having relevance. Otherwise, you know, you don't have to worry. I mean, you don't have to do this asymptotic analysis. Asymptotic analysis, so for smaller input, if your application is having only smaller input, you can just do the step count analysis. That is enough, and accordingly you can compare which is better and all. So that we can do. Okay, so it's not a big deal. But you know, when it comes to larger size of the input, definitely asymptotic analysis that matters a lot. Okay, so that is going to give a very simple analysis technique. And now when you are having asymptotic analysis, the running time typically we express in asymptotic notation. And let me tell you, this big O I am telling you for a long time, it is an asymptotic notation. Similarly, we have to study 5 notations totally, then big O, then another one is big omega, and there is something called as the theta notation, and there is something called as small o, and there is something called as the small omega. So these 5 things you are supposed to study. So in this video I will try to cover this big O, then maybe in the next video big omega and theta, next one small o and the small omega. So like that I am planning. So big O notation, you know, it gives the asymptotic, again asymptotic analysis only we are focusing. So asymptotic upper bound. Okay, so this is something for the worst case analysis. And now what about the big omega? It is going to give asymptotic lower bound. Okay, and theta is going to give you asymptotically tighter bound. So that is always the case. Okay, now what about the small o and small omega? It resembles like big O and big omega, but the thing is that, so yeah, we will see when we are defining the small and small omegas, they are also going to give this say small o and big O together, they are giving upper bound of the algorithm. And similar to this omegas, we have small omegas that will give you the lower bound. Okay, so so for finding upper bound we have big O and small o, for lower bound we have big omega and small omega. But still let me tell you what is the difference very clearly very soon. Okay, so basically this bigger notation like big O, big omega, theta, they are all tighter bounds, right? So the small and small omega, they are going to give a slightly looser bounds. Anyway, we will see with the formal definition, you will understand this. So all these things are mathematical concepts. So we have the formal mathematical definition for them that you have to understand and you have to apply in a given problem. So asymptotic notation is to describe algorithms asymptotic running time. So this is only when you do this asymptotic analysis, not for another algorithms asymptotic running time. Okay, so that you have to be careful. Then asymptotic notations are defined in terms of functions whose domains are the set of natural numbers. Typically we have a function, right? What about the domain? So we are assuming some integer value. Anyway, we will see some more examples, it will be clear for you. Recall that we characterized the insertion sort as something a n square plus b n plus c for some constant a, b, c. Now by writing this insertion sort running time as just theta of n square. So that also, if you don't know the meaning of theta, we will see soon. Okay, it is a tight bond. If that is the case, we abstracted away some details of this function. Okay, so always that abstraction is happening. So that is why we shifted from step count analysis to asymptotic analysis, because always more 99% of the time the requirement is like you want to compare two different algorithm and you have to choose the best, and that time these things are going to help. Okay, so the because the asymptotic notation applies to function, what we were writing as theta of n square was something like this. Even though we are writing like theta of n square, uh, uh, you can express it as a function like a n square plus b n plus c, but from this only we got it. But just I just want to tell, like, asymptotic notations are basically applied to functions. So just like you are applying to any function of n, you can apply here also. Here it will be like n square or maybe some bigger term also. So we will see that. So which in that case happen to characterize the worst case running time of insertion sort. So this is going to give you the worst case running time. So hope it is clear. So what we tried is, we tried to go through the basics of asymptotic analysis. Right now it's time for us to see each notations in detail. Starting with the first notation, that is big O notation. So I request all of you to go through the definition and understand it very precisely, say by looking at the structure or okay, so it's a mathematical concept. So just try to visualize yourself, then I will be explaining. See how big O is defined. See how formally the notation big O is defined. As I already told you, it is going to give you the asymptotic upper bound. Okay, so how we can mathematically define it? So this big O of a function g of n. So basically, what is g of n? G of n is a function in n, right? So typically, you can visualize it as some step count of some algorithm, something like that. Okay, so basically, we are getting step count as some function of n, where n is input size, like that. So basically this big O is going to give you a set of other functions. So these are also some kind of step count. So it may be in the abstracted form or in the expanded form. So basically both are functions of n. So you can, so what so far what we are familiar is the step count we expressed like this. Okay, so anyway we got it right. So mathematically, so given any function in n, what is this big O? So its big O is defined as set of all functions, again some other function, say f of n, and the requirement is like this f of n and g of n should be related like this. F of n is less than or equal to some constant c into g of n. So this is very important. Okay, so this g of n is a upper bound or bigger than this f of n. So what does it say? So g of n is something bigger. Okay, so I can say that f of n is equal to, its upper bound is g of n. G of n is bigger, so the upper bound is denoted by big O. Okay, big O of g of n. Okay, I can express this f of n as big O of g of n. So mathematically, what does it says? F of n is smaller than g of n with some constant difference. So you can think of a constant here. Okay, so that about it. So f of n is actually big O of g of n, provided this condition is true. Okay, now focus on any g of n. Many people will be having this relation with this g of n, right? So you can map different function as big O of g of n. For example, let me just tell you some examples, like say this a n square plus b n plus c. Is typically, I told you, it's something like a big O of n square. Okay, so now you can vary this constant, like sometimes it may be some constant c1 into n square plus some another constant c2. So this also you can write as big O of n square. Now some c1, some c3, I'm varying constants, that's all, n square plus c4 into some log n. So the log n is asymptotically smaller term, right? Is this n square is a dominant term here also, big O of n square. So what I'm saying is this big O of n square is equal to set of all f of n. So in that set, this a n square plus b n plus c will come, and another candidate is like the c1 n square plus c2 will come, and another candidate is like c3 n square plus c4 log n will come, etc. will come. So this is a set. So that is what. So many people will have this upper bound as n square. So that is a meaning. So I'm saying that upper bound of something is n square. So there are many people for which you can map to this n square. So anyway, at this point, all this dominant term is n square. But mathematically, you have to show this kind of a relation. This f of n is less than or equal to some constant c into g of n. Now what about the c and c? There exists a positive constant. So it's enough for you to show some constant for this. Okay, so you don't have to say that it is true for all constants, nothing like that. There exists a positive constant. So first of all these things are positive. The functions you have to assume, like we are talking about the positive functions of n only. So that is why here this 0 less than or equal to, like that we are writing, because we just want positive functions only, whether it is f of n or g of n, all are positive functions of n. And also this constant c is also a positive constants we are talking about, right? So it can be integer or real, but I need a positive value. Okay, now one more thing, so that is again very important, that you have to find out another positive constant that also there exists only. So there exists this is something important. There exists one constant c for this relation and another constant n0, right? And this n0 is something important, such that this condition is true, and this condition is true for all values of n greater than or equal to n0, something like that. So if I can establish such a relation, I mean, you have to find out a c and an n0, and you have to say that f of n is less than or equal to some constant c, which you find out, into g of n for all values of n, I mean input size greater than or equal to n0, then only you can say that f of n is equal to big O of g of n, or big O of g of n is having that f of n as a candidate or member. Okay, so at this point I can say that this g of n is the upper bound, right? So g of n is asymptotically upper bound for f of n. Okay, yeah. Now the significance of n0 I will tell you, say with an example. Some simple example we will take. Okay, so what I'm trying to say is, let me give you two functions. So this f of n, I am saying that it is n square, and g of n, I am telling you like it is 2 power n. Can you tell me which is bigger? I think most of you are knowing this 2 power n is bigger, right? Now if you don't know, or I just want to give you more insight into that, just like what I'm doing is something. Suppose you don't know which is bigger, what you will do, you will try with the different values of n, right? So input size, so starting with the smaller value, because you don't know which is how to compare from which point onwards. So when you are doing like this, you can see that 1 n square is 1, 2 power 1 is 2, so this is found to be large. So that is our conclusion. Then now when n is equal to 2, you can see that here you are getting 4, here also you are getting, so both are looking same, right? N is equal to 3, you can see here you are getting 3 square, that is 9, here it is 2 power 3, that is 8. So this is large. Now something you are getting confused, right? Which is large, like that. If somebody is trying this way, because you as you already know this is bigger, because you may assume some bigger value of n, then it is okay, because that is the correct way to do this analysis, right? So we know this, okay, but now we are establishing with the assumption that we don't know, so, and we are trying with the different values. Okay, now when n is equal to 4, you can give 16. Now from this point onwards, whatever be the value you are giving, for example here you are getting 25, here you are getting 2 times of it, like this. Now when n is equal to 6, so here is equal to getting 36, here you are getting 64, which is much large, etc. You try any value, say n is equal to 10, here you are just getting 100, 10 square, here it is 2 power 10, that is 1024, it is much large, right? So like that it will grow. So what I'm trying to say, I know that this g of n is greater than or equal to f of n, something like that, or let me write like the way I written, f of n is less than or equal to some constant c into, so here value itself it's saying, say c is equal to 1, like that you can take g of n. So for a value of c it is found to be true, right? So c because I directly compared without considering this c. Okay, and this is true for all. At this point it has to be very clear, like n greater than or equal to n0. So what is my n0 here? My n0 here is this 4. Okay, so this is important. For all n greater than or equal to n0, from this point onwards I can have this kind of a conclusion. Okay, So the functions can be anything, we don't know. So for example, I'm just randomly drawing. This is not about n square or 2 power n, or it can be some two functions in n, or two polynomials in n. You know that, say something like this. This is growing like this, and another function, when you observe, it's growing like this, and you know that this is growing faster than. I mean, this order of growth is more than this f of n, maybe with some constant times, okay, like that. But you are reaching that conclusion after some value of n only, right? Say n is equal to n0. X-axis you are taking input size, and y-axis you are taking, say, the step count, okay? So the complexity which you are expressing in step count. So this is what you are saying. So it is something like f of n is less than or equal to some constant c into g of n, and of course they have to be positive, I mean 0 less than or equal to, like that. And for all n greater than or equal to n0 only. So what is this n0 is, sometimes they can ask you such a question also. So I hope you got an idea right now. Okay, so that about it. So like that, all these parameters are equally important. Now what I'm doing is, I'm just taking one example here. Say, let me take f of n is equal to some 3n square plus 5n minus 2. I'm randomly picking a value. Now I just want to say what is this. It is the order of n square, but I'm just trying to tell you it with the help of c and n0. Okay, so formally, if in exam they're asking you to give the asymptotic upper bound of something, you have to give the mathematical definition. Okay, you can write the definition, and you can tell for this function this is c and this is n0, like that. So let's try with that. We don't know, so can you guess what will be c? So what we need is like a 3n square plus 5n minus 2. The dominant term is n square, so I need something bigger than this. So if I'm taking something like a n here, it's not going to match, because n square is a dominant term here, right? So g of n should be minimum n square, or it can be maximum anything. Okay, so because I'm looking at an upper bound, okay, so if you're taking n cube, definitely it may be bigger. Okay, so you can have this relation with many functions. We will see one by one, but you don't take like say like, so if you are taking like n, whatever be the constant you are taking, this is like, okay, so if I'm taking something like some c into n, if you are taking, see, this condition is not going to be true, so that right, because here some bigger term is there, n square. So if you try to make it bigger, as it is n only, whatever be the bigger constant you take, this n square is going to beat it. So this is not going to work. Okay, so what we need is something, definitely this, when I'm writing it say, what I can do is, my guess is like a big O of some g of n. So that g of n I'm trying to find. G of n is not going to be this n. Big O of some n square at least I need, right? Or plus some epsilon, whatever it is, for some epsilon greater than 0. Finally I'll be getting something like this, or maybe n square log n, or something bigger than this n square is what I'm expected. So it is at least this at least n square. So it is greater than or equal to 0, so that when you are putting it as 0, you will get it as n square. So that guess I am having. Okay, now with that in mind, let me try. For example, I am trying with say 3n square plus 5n minus 2 less than or equal to n square. I'm just trying to see whether can I write it as n square. So I need a constant here, right? So what I'm doing is, so can you guess what is a good candidate for this constant here? So can I put 2 here? Will it work? It's not going to work, because here it is 3n square, here it is 2n square only. So definitely it is never going to be a bigger quantity, because 3n square, that 3 will dominate always. Fine, if you are putting any value here which is lesser than this 3, it is not going to work. Okay, now what you can do is, you can say try with the, so this 3 is also not going to work, because if you are putting, so will it work? So I'm just telling you all possibility, like how you will be thinking. So 3n square is okay, 3n square is okay, but this is something dominating, right? So this is also not going to work. Fine, I'm just eliminating all wrong answers which you may try. Okay, so one possible candidate I have is like 3n square plus 5n minus 2 less than or equal to some value bigger than this 3 is going to work, like even 3.1 will also work. But in that case also you have to try with all n, some bigger value of n you have to find out. So for safer side I am taking this C as 4. Okay, so that's something a nice guess I am having. What I need is there exists a positive constant C. This 4 is enough. I just want to show a single constant, that will work. Okay, so let it be 4n square. Now what you can do for making this inequality true, so you can try with the different constants. Okay, so the requirement is like it should be some value bigger than this 3, and if it is let it be some 4. Now can you tell me what is it is true for all n greater than or equal to n0? So what is this n0? So that is my question. So you can try with a different value. Is n0 is equal to 1? Will it work for 1? So definitely for 1, here I am getting 3 plus 5 something, it is bigger, so it is not going to work for 1. Then n0 can I work for will it work for 2? Here you are getting you have to try. Okay, so like 2 square 4 into 4 16 you are getting, but here you are getting 12 plus 10, that is 22, so it is not going to work. Okay, fine. So n0 is equal to 3, will it work? So here I am getting 3 square so what is 3 square? 9. 4 into 9, 36, right? So here I am getting 36. Here it is 27 plus 15, 37. I think this is going to work. Okay, so so when I am putting this n0 is equal to 3, I will get 3 into 9, it is 27, plus 5 into 3 15, minus 2, is it less than or equal to 4 into 9, that is 36. So what I am getting here is 27, this 37, sorry, it's beating, right? It's 42 40 something I am getting. So this also not going to work, so I don't have to write it. Anyway, that condition also violates, so definitely maybe the next value will work. Let's see. So is it true for n0 say is equal to some value like 4? Okay, so 4, let's see that when I'm putting n0 is equal to 4, 3 into 16 into 3, 48 plus 20 minus 2 at one side, is it less than or equal to 4 into 16, 64. So here it is 48 58 68. Oh god, 68 minus 2 is 66. Again it's not going to work. Fine. So definitely that n0 is equal to 5 is going to work. This is also not going to. So this is the way you have to try, or you can directly start with some. So because you know why, what we need is I just need an n0. So if you want, you can say that n0 is equal to 10. It may work. Okay. So what I am trying to see is some very tighter value for this n0, but that is not mandatory when it comes to exam. You just have to show a particular value of n0. That's enough. So will it work for n0 is equal to 5? Let's see. 3 into 25, 125 plus 25 minus 2, is it less than or equal to that 25 into 4, it's 100. Again it's not going to work. So I made a mistake actually. 3 into 25 was 75. This is going to work, I think. So n0 this is 25 into 3. 25 into 3 is 75 minus say this is 75 plus 5 into 5 is 25 minus 2. Is it less than or equal to 4 into 25? 100. Yes, this is true, right? Because 75, this is 100, so this is 98. Fine, so this is going to work. So the correct value, I mean it's not like that. So what I can say is so the conclusion is 3n square plus 5n minus 2 is less than or equal to some 4 times n square for all n greater than or equal to 5. Onwards it is correct, but same inequality I can write like okay, let me take a new page and tell you. Okay, let me take something here. So what we got is 3n square plus 5n minus 2. 3n square plus 5n minus 2. it is less than or equal to some constant c which I taken like a 4 into n square for all n greater than or equal to 5 is what I obtained. So this is this is enough. So with this, for a value of there exists c is equal to 4 and n0 is equal to 5, such that this condition is true, right? So I established that relation. That is enough. So from that I can say that 3n square plus 5n minus 2 is equal to, is upper bounded by this n square, because I got it right. So there exists a constant c is equal to 4 and n0 is equal to 5. But will it work for so can I say that there exists a constant c is equal to 4 and n0 is equal to 6? See, still it is correct. Fine, because for all n greater than or equal to 5, or for all n is greater than or equal to 6 also it is true. Okay, so like that, I can try with a different constant also. If you are, so here you systematically try like that. If you want, you can try with the c is equal to 5, and accordingly you tell me what is your n0. Okay, so like that you can try with any bigger values. Okay, so basically there exists a c that is 4 plus not 4 plus 3 onwards. Okay, some bigger value of 3 is what I need, some 3 plus some epsilon, something like that, and n0. So n0 you have to try out. So for different values, so this is going to work for, so 3 plus epsilon onwards. So when you take this epsilon like 1, you got like this epsilon as 2, you will get some different relation. But anyway, I just need a value of c and n0. So this is going to work, and just try to find out what is n0 here. So definitely this is also going to work. Okay, so that you can systematically explore, or you can try directly with a bigger value of n0. That also fine, like say 100 or 1000, so that the process may be easier for you. Anyway, you got it right. So how we can write it? So now the conclusion is, so this is not only here. What I got is like, now the let me ask you the question. 3n square plus 5n minus 2, is it less than or equal to some constant c into n cube? So definitely, right? So I am just asking you to try out. So just find out a c there. You can try with that c is equal to 1 itself. Okay, so if I am saying like a c is equal to 1, say c is equal to 1, see what will happen here. 3n square plus 5n minus 2 is less than or equal to n cube for all n greater than or equal to what? That you have to find out. So when I am giving it as 1, it is not going to work. 2 cube, yeah, it's not going to work. 3 cube is 27. This side also I am getting 27, so it's not going to work. Plus something. Okay, 4 cube is 64. Here it is 16 into 3, 5 into 3 minus 2. This will work, right? So I think for all n greater than or equal to 4 is going to work, because here I will get 4 into 16, right? Sorry, 3 into 4 square, 16. 48 plus 5 into 4, 20 minus 2. Oh, sorry, and this is 68 minus. Okay, fine, it's not going to work. Anyway, I may make some mistake. I just want you to understand the process. Okay, so can you try with the n0 is equal to 5, just like the previous case. So yeah, n0 is equal to 5, the relation will be like 5 square, 25, 75 plus 5 into 5, 25 minus 2. Here I am getting 125, so definitely it is going to work. Okay, minus 2, fine. So like that. Okay, so like that, whatever be the bigger quantity you are taking, it is going to work. Okay, so let me just tell you, like same function, if I am writing 3n square plus 5n minus 2, it is big O of n square, and the same thing is big O of n cube, the same thing is big O of n square, say n raised to 2.5. That also fine. I just want some bigger value of n square, like n square or more, say n square log n. So like that, many relations you can establish. So all these are asymptotically upper bound to this 3n square plus 5n minus 2. So this is something 3n square plus 5n minus 2 I got as step count for my function, for my algorithm. Then I can say that my algorithm, so this is something special, this is the, out of all this value, this is a more closer value. So I can say that this is asymptotically tighter. But what about all these? All are asymptotically looser. Okay, anyway, keep this in mind. So from this point we have some looser bound also we formally define using something called as small o. Anyway, we will see in the subsequent session, and that time I will ask you like what is asymptotically tighter bound and looser bound. So like that many things you can write, so you can keep continuing like, so this is equal to big O of 2 power n because it is bigger, big O of n raised to 10 or n raised to 100, all those things you can try out, right? So it's a big list. Similarly, if you focus on what are all the things you can write as big O of n square, that is also going to be a list like this, because big O of n square itself, there are many functions. That is how it is formally defined. So hope you are clear about the definition. Now you randomly take some function and you try to see it is big O of what. Okay, something like that you can try now. Yeah, and try some example. I think I can you can just okay, maybe let's take something like I'm trying to give you some different example. 1 second. Now let me take a different example. Say, so the given function f of n is given to be some 5n cube plus 6n square into say 2 power n minus 100. Just randomly taking, you can take I can, or you can assume anything. So maybe they were wondering like, so this is step count analysis of some algorithm, we don't know what about it. So you can visualize it like it's having some 3 modules. One module is taking some 5n cube, running time maybe because of 2 4 loop something. So here it is doing some kind of enumeration kind of things. Say 2 power n, for a set with n element, 2 power n subsets are possible. Suppose it is trying to do something like enumerating all subsets and doing some processing over the subsets, then and the processing might be taking some n square time. I'm just trying to give a meaning for this. It can be anything. Okay, you can think of any procedure which is taking this much time, and another module of some constant time. Now what is an upper bound for this? So as it is obvious, here it is n cube, here it is n square, but this 2 power n is coming, right? This is an some constant. So you remember this always, some n raised to some constant k, and some another, so k1 is one constant, k2 is another constant. Okay, k2 raised to some n. So whatever be this k1 and k2, this quantity will be always greater. Okay, so keep again, because what is happening here, this n is getting multiplied some constant number of time. N raised to k1 means n into n into n, k1 times. Here the constant is getting multiplied some n number of times. As you know, n is a variable. How big is this n? That many times the constant will get multiplied, right? But how big is the n? The n is getting multiplied some constant number of times only. So that is why this value is getting smaller than this. Okay, you may take some examples and you can visualize it, but still it is something general thing that is happening mostly. Okay, so for positive constants k1 and k2, so in that way, n cube, whatever be this quantity, this 2 power 1 n will dominate it. So definitely this multiplicative term will be dominating the whole thing. So out of this n square 2n, you can ignore that constant coefficient 6, but you are not supposed to ignore that n square. So what on judgment one can have is this will always be less than or equal to some constant c into n square into 2 power n. One can write like this, right? So you can try with some values of this c and n. So I'm just giving you some value for this c. You can just put c is equal to 10 and n0 is equal to some 4 1 onwards. I don't know, you just check it. Okay, so it may be some other. If you want, you can give value like 1 2 3 4 etc, and you can find a very closer value. But anyway, as for big O notation, we just need there exists a c and there exists an n0, such that this is true for all n greater than or equal to n0. Something like that is what we want to establish, right? So that is enough. Now you can see that the same quantity, you can show like so by this you can say that it is so because of this you can say that this quantity, I mean your f of n, that is 5n cube plus 6n square plus 6n square into 2 power n minus 100, and this particular quantity is some big O of n square into 2 power n, right? Or if you want, you can say the same quantity, some bigger value you can assume, like n cube into some 2 power n, or this is equal to some n square into 3 power n, or some big O of n cube into 3 power n, like that you can assume anything. So what I was trying to say is, it is something, it should be some minimum n square, that quantity should come, and along with that, even though you add some n raised to 2.1, that also fine, some epsilon, like that. Okay, and another one, here it is minimum that 2, and 2.1 onwards, like you can think of any delta, some constant value, and accordingly raised to n. So like that you can write it, and this will happen for all n greater than or equal to n0. You can find out some c and n0 always for this kind of a relation. Okay, and what about this epsilon and delta? Epsilon greater than or equal to 0, and this delta also greater than or equal to 0. So this is how this so now you know, right, given any function, what is the upper bound of it. Just look at the dominating term. All terms which are equal or above this dominating term will be the big O. So it is going to give you the upper bound, and out of all this you can see that this is a tighter upper bound. Okay, I mean, strictly speaking, any value less than this is not going to be a big O. And all these values will satisfy the definition, mathematical definition of big O notation. So that about big O notation, I think you can take more and more examples. You try with any value. Say, let me take one more example for you. Say another one I can show you is like, so this is my f of n. F of n is equal to some n log n plus some constant, like that. Okay, so this will be something big O of n log n. Okay, so this is the dominating term. Now the same thing you can write like a big O of even n log n. Log n I am upper bounded by n, so that it will be something like n square. So now big O of even something 2 power n, anything you can write. Okay, so can I write it as a big O of n? So that is wrong, because the minimum it should be n log n. Okay, so when you write like this, that is going to cross the relation. Or I can't write it like a big O of n log n is fine. If I am writing like log n, it is not going to violate the relation. Big O of n log n into n log n. I mean, just I multiplied it with one more log. Here I am taking logarithm of logarithm, so that is a smaller quantity. So now this is equal. Okay, fine. Like that you can try with a different value. On essence, it is some value bigger. It's an upper bound, asymptotically upper bound. Okay, so any value which are equal, or I mean the dominating term and bigger terms are making this big O relation. Now similarly we will see about this big omega and the tight bound, that is theta, and then the small omega and other things. So here, here also this is a tighter bound. So tighter bound is typically expressed by big O only, but when it comes to looser bonds, we have one more notation for capturing this all these looser bonds, and that is the small O. Okay, that we will see soon. Smaller notation, like that. So but for tighter bond, only this big O is the option. Okay, so that about it. Yeah, here I thought of giving more examples. I written some here. Okay, fine. So thanks for watching.